In this talk, I will introduce our work generating virtual reality stroke gesture data from out-of-distribution desktop stroke gesture data. I'm Lin-Ping Yuan from Hong Kong University. This work is collaborated with Hong Kong University Guangzhou and Microsoft Research Asia. When users use VR applications, they will generate much interaction data. For example, their gaze, hand, and body movement. The data can be analyzed and utilized from different perspectives to serve various stakeholders and purposes. For example, UX designers can provide users with stroke gestures as intuitive user input. Researchers can visualize users' movement to get insights on space usage patterns, and storytellers can utilize the gaze data to refine their design of virtual scenes. However, the collection of VR interaction data faces various difficulties, such as a small user base, frequent deployment failures, and inconvenient collection setup. Thus, as pointed out by previous studies, current VR interaction datasets are mainly derived from a small number of participants in lab settings. In other words, the current VR datasets are often insufficient and lack diversity to support downstream applications. For example, since there are no large VR stroke datasets, a VR drawing application can only train a classification model on 2D strokes, whose accuracy on VR strokes is low and diminished user experiences. To alleviate the difficulty in obtaining VR data, previous studies have investigated various techniques to synthesize VR stroke data. These approaches are efficient and scalable to increase quantity. However, diversity is still restricted because they only rely on existing VR interaction data as model input. To address this limitation, this study investigates whether and how desktop interaction data can be used as an alternative sources of model input. Stroke gestures are selected as our primary focus. So why do we consider desktop stroke gestures as an alternative input? It is because they can be collected from crowdsourcing platforms that are accessible to numerous users with easy setup. Thus, they can add diversity to the VR stroke dataset with different shapes drawn by different users. So why is it possible to use desktop strokes as alternative input to generate VR stroke gestures? This is because we find some commonalities between VR and desktop strokes, such as features related to the XY plane, like velocity and curvature. Where VR strokes present additional dimensions, such as Z vectors, the existence of the commonalities enables the generation of additional dimensions. But it remains unknown how to achieve the generation. Thus, this work aims to explore how desktop strokes can enrich VR strokes datasets while preserving the original characteristics. To understand the problem better, we first conduct preliminary studies. With both VR and desktop stroke datasets, we perform processing and feature extraction. We extract 15 features that they have in common. Then, we perform data analysis regarding commonalities and additional dimensions. We have some interesting findings, so let us look at commonalities first. This figure shows the t-SNE and KDE plot of rectangles and circles collected from VR and desktop environments. As we can see, distribution shifts exist not only between VR and desktop datasets, but also within VR datasets or desktop datasets. We further plot circles drawn in different speeds, which also present different distributions. Thus, the distribution shifts are induced by various factors, such as input environments, stroke shapes, speeds, and other unknown factors. The distribution shifts bring a challenge. It is hard to generalize the models trained on VR strokes to desktop strokes that comes from unseen distributions. Now, let us look at the additional dimensions of VR strokes. The figure shows Z vectors of VR circles and VR arrows, with each line a Z vector. We can see that Z vectors spread out the entire output space and overlap between different stroke types. This brings the second challenge. It is hard to capture relationships between commonalities and additional dimensions from small original VR datasets. With these insights, we formulate the problem of generating VR strokes based on desktop strokes as a conditional time series generation problem. In other words, we generate additional dimensions conditioning on commonalities. We propose a two-stage method to achieve this. In the first stage, we learn relationships between the commonalities and the additional dimensions by training on VR stroke datasets. We use a SIGAN network. In the second stage, we take desktop stroke datasets as input, which provides commonalities, and use the trained generator to synthesize additional dimensions. By combining the common parts of the desktop strokes and the synthesized additional dimensions, we can obtain enriched VR stroke datasets. To address the first challenge, we further formulate the problem as a conditional time series generation problem under out-of-distribution circumstances. Specifically, we propose a conditional domain-invariant generator, which leverage out-of-distribution generalization techniques to deal with the distribution shifts. Now, let's dive into the details of our generator design. As we showed before, VR strokes are drawn from different distributions. Thus, rather than training the generator by assuming all VR strokes allow one distribution, we characterize the latent distributions within the VR stroke dataset with these two steps. The intuitive idea is to group all the VR strokes into several latent domains, whose distribution gaps are maximized. Since many known and unknown factors, such as shapes or joint speeds, cause the distribution shifts in a joint way, we do not obtain the domains based on individual factors. Instead, we use a domain classifiers to perform k-means clustering on class-invariant features distilled by the network. The next step aims to learn domain-invariant representations and enable the trained encoder-decoder can generalize to unseen distributions. To achieve this, we utilize adversarial learning to fool a domain discriminator that classifies domains. If the discriminator cannot differentiate between strokes from different latent domains, it indicates that the encoder has successfully learned domain-invariant features. In our generator, the step 2 and step 3 rely on the feature extracted in step 1. As we mentioned before, the Z vectors spread out the whole output space, making it hard to capture the relationships. Thus, we propose to cluster Z vectors to discretize output space, and thus we can treat the VR strokes as discrete classes rather than continuous vectors. To evaluate the generalizability and examine the influence of training data size, we compare our method with 3 baselines. Similar to our method, these baselines are also based on conditional GAN frameworks. However, they do not integrate advanced techniques as we do to deal with the distribution shifts. When conducting the experiments, we ensure that the training and the testing sets are with different distributions by ensuring that their shapes do not overlap. As the table and figure show, Our method consistently outperforms the baselines across all metrics and data sizes. We also conduct ablation studies. The table and the t-SNE plots demonstrate the effectiveness of our proposed output space discretization and the loss functions of the generator. Lastly, we developed two applications that use the synthesized VR datasets. In the application of VR stroke prediction, we predict the next VR stroke users might want to draw. The figures show the results of the model trained on large synthesized VR sketches and the limited real VR sketches, respectively. It indicates that our approach can make the prediction task possible with synthesized VR strokes, although the task is impossible with limited real VR strokes. Thus, it reduces the burden to collect real VR strokes. In another application, we aim to classify digits 0 to 9 drawn in VR with different classification algorithms. These tables shows the accuracy of deep learning classifiers. We can see that the deep learning model can achieve satisfactory accuracy with synthesized datasets alone. And this figure shows the results of template-based classifiers. Generally, adding synthesized data can improve their accuracies. However, accuracy may decrease when the amount of synthesized data exceeds a threshold. The differences imply that the use of generative VR strokes in downstream applications needs to consider the characteristics of specific algorithms. Now we summarize take-home messages. We distill two lessons learned for generating other types of VR interaction data. First, we need to consider whether and what commonalities and additional dimensions exist. Then, we need to pay attention to distribution shifts. We also reflect the use of VR and desktop datasets. For more details, please refer to our paper. We plan to extend our methods from planar VR strokes to non-planar VR strokes, which are important in industry design. This may involve the proposal of novel reference frames and the reconsideration of the commonalities and additional dimensions. We have released our code and datasets. If you have any questions, feel free to send emails to me. Besides, I'm on the job market this year. If you find my research aligns with your interest, I would love to talk with you. Thank you for listening.